Welcome to today's Explainer. We're jumping right into a pretty wild puzzle today. We're going to look at something you've probably seen 100 times, but we're going to examine it at the microscopic level. What exactly is going on when matter just seems to, well, disappear right in front of our eyes? It's like a magic trick, but it's pure science. We'll be using some really cool models to track this unseen universe, and honestly, by the time we're done here, you're never going to look at everyday chemical reactions the same way again. Let's get into it. Picture this. You drop a solid bath bomb into a tub of water. You know the drill, right? It immediately starts fizzing like crazy, bubbling up, releasing all this gas. And then, a few minutes later, that heavy, solid sphere is just gone. Vanished into thin air. Or, I guess, vanished into the water. It drops us right into our big mystery. I mean, our eyes are telling us the solid is gone, that the matter itself has disappeared. But we know things in science don't just magically blip out of existence. So, what is actually happening in that water? Okay. Before we play detective, let's get a couple of basic terms straight so we can properly track what's going on. First up, we've got reactants. These are literally just your starting ingredients, the stuff you have before anything happens. In our case, the dry bath bomb and the water. Then we have the products. As you may guess, these are the brand new substances produced by the reaction. If we're going to figure out where our missing matter went, we have to do a strict comparison between our starting reactants and our final products. To figure this out, scientists rely on models. Now, an initial model might just use simple colored circles to represent the baking soda, the citric acid, and the water. It's a decent start, kind of gives you the basic idea. But actually, scratch that, it's just not detailed enough for us. If you look at the revised model, we've swapped out those simple circles for actual molecular structures. We have to do this because to truly solve where the matter went, we need to know what those tiny particles are doing down at the atomic level. We literally need to see the exact pieces we're playing with. Which brings us to the absolute core question of this whole explainer. As that bath bomb fizzes away to nothing, where do the atoms actually go? Did they just pull a disappearing act? Are they gone forever? Or are they just hiding somewhere else in the mix? Well, to answer that, we have to look at one of the fundamental rules of the universe. Atoms are essentially indestructible building blocks. Think of them like Lego bricks. Let's say you build this massive, complex Lego spaceship. Then you smash it to pieces on the floor. The spaceship itself is gone, sure, but every single individual Lego brick is still sitting right there. You could easily take those exact same pieces and build a completely different structure, like a castle. The spaceship transformed into a castle, but you didn't lose a single brick, and you definitely didn't magically spawn any new ones. Chemical reactions, they work the exact same way. The atoms are simply rearranging themselves. So, let's apply that Lego logic to our bath bomb. Look at our reactants. We start with baking soda, citric acid, and water. Now look at our products. What's left after the fizzing stops? We end up with sodium citrate, water, and carbon dioxide gas. Here is the wild part. If you were to break all those molecules down into their individual atomic building blocks, all the carbons, hydrogens, oxygens, and sodiums, you would find that the types and numbers of atoms match up perfectly on both sides. That carbon dioxide gas bubbling away, it's literally made from the exact same carbon and oxygen atoms that used to be locked up inside that solid bath bomb. Absolutely nothing is missing. So here is your big takeaway, the unbreakable rule. In any chemical reaction, the amount of matter you have at the beginning in your reactants is the exact same amount of matter you have at the end in your products. Mass is conserved, period. No matter is lost, and absolutely no new atoms can appear that weren't there from the very start. Everything that was in that solid bath bomb is still right there in the bowl or floating in the air just above it, just rearranged into new formations. Let's look at the ultimate microscopic audit. Now, don't let this chemical equation intimidate you. It's really just a recipe. See that ratio? It takes exactly 1 molecule of citric acid reacting with exactly 3 molecules of baking soda and 3 of water to make this work. When they react, that's what the arrow means, they rearrange into exactly 1 molecule of sodium citrate, 6 waters, and 3 carbon dioxides. If you sit down and tally up every single C, H, O, and Na on the left, it perfectly matches the right side. Every single atom is completely accounted for. But hang on a second. Let's think about this. We know carbon dioxide floats away as bubbles, right? And water is, well, water. But our equation just proved we created a brand new substance, sodium citrate. And sodium citrate is a solid. So, if this new solid product was just created right there in the bowl, why can't we see it? Why does the remaining water look perfectly clear? The answer, it dissolves. We can't see the newly formed sodium citrate because it's highly soluble. When it forms, its particles instantly disperse and mix completely in with the water particles. This is just another fascinating way particles behave. They didn't vanish, they didn't react to form a gas, they just rearranged themselves into a mixture, spreading out so incredibly thin that our naked eyes just can't see the solid pieces anymore. Now, let's zoom out for a second because this concept is huge. Chemical reactions, like our fizzing bath bomb, they aren't the only time particles do this little rearrangement dance. This invisible shuffling of atoms and molecules actually drives a bunch of other physical processes that we see every single day. Take phase changes, for instance. Think about boiling a pot of water on the stove. When that liquid water turns into steam, you aren't creating some brand new substance. It's still just H2O. What's happening at the particle level is that the heat is causing the water molecules to speed up and spread way far apart from each other. The molecules themselves stay totally intact. The hydrogen and oxygen atoms are still holding hands, but their arrangement in space completely changes. When we put these three chemical processes side by side, a really powerful pattern jumps out. With chemical reactions, the atoms themselves rearrange to form totally new substances. With phase changes, the molecules just move closer together or further apart, but no new substances are made. And with dissolving, particles rearrange to form a uniform mixture. But here is the absolute most important thing to remember. No matter which of these three processes is happening, they all share one major secret. The matter never leaves. The particles are just rearranging. So the next time you toss a bath bomb into the tub, or boil water for pasta, or even just stir sugar into your morning coffee, think about what's really happening. You are watching the unseen universe constantly rearranging itself right in front of you. These tiny, invisible, microscopic audits are happening everywhere, constantly balancing the books of matter in our kitchens and in nature. Literally nothing is ever truly lost. But before we wrap up, I want to leave you with a slightly different mystery to chew on. Okay, so we've totally nailed how matter rearranges, but what about how we experience it? Different bath bombs have wildly different smells, right? Lavender, citrus, eucalyptus. If odor is just a property of these rearranged particles floating up into the air, what exactly is going on at the microscopic level when you smell something different? How do these specific little molecular shapes physically interact with the receptors inside your nose to make your brain say, oh, hey, that's lavender? That's a huge mystery and definitely something to think about for next time. Until then, stay curious.